Yeah, in previous lecture, we studied for the Ginzburg-Landau theory and the zero magnetic field case. Now we are starting from the applying magnetic field case. And I do not know the name, the order. Yeah. Anyway, 6 flux quantization. Now we are dealing with the applying magnetic field, and anyway, the order parameter is written down as a magnitude for the order parameter and the phase factor. It is order parameter. And also from the Ginzburg-Landau equation, and the second Ginzburg-Landau equation gives the current has the H bar E star and phi star gradient phi minus phi gradient phi star minus E star square A and phi square. This A is the vector potential, and the existence of vector potential indicating with applying magnetic field. Therefore, we should calculate this equation, and also here in the gradient we should calculate the gradient phi. Then in this case, in the I phi gradient theta plus exponential I theta gradient phi r, and also gradient phi star is that minus I phi gradient theta plus exponential minus I theta gradient phi star r. Therefore, from this Ginzburg-Landau equation, and this term should have the phi star gradient phi minus phi gradient phi star, and it should have the phi star exponential minus I theta, and gradient phi is that I phi gradient theta plus exponential I theta gradient phi r, and minus phi r exponential I theta, and gradient phi theta is that minus I phi gradient theta plus exponential I theta minus I theta gradient phi star. And from this equation, and it can be write down, and also this term and this term cancel with each other, and also therefore it is 2I phi square and gradient theta. Therefore, this second Ginzburg-Landau equation say that J is that H bar E star and 2I cancel each other, M star and phi square gradient theta, and second term is minus E star square over M star A and phi square. Let's divide this in both sides, and also and have the line integral. Then it is M star over E star square, and also J over phi square and line integral dot dl is that this term M star E star square changes by h bar over e star, and line integral for gradient zeta dot dl minus line integral a dot dl. Then from this, and the line integral gradient zeta dot dl is that gradient the zeta dl dot dl. It is d zeta line integration is 2 pi n. Here is n is integer, and line integral a dot dl is that from the divergence theorem is that surface line integration becomes a surface integration of the b dot ds, and it is a flux, magnetic flux. Therefore, it can be write down as the m star over e star square line integral j over phi square dot dl, and this is phi flux plus flux phi is that it is the 2 pi n 2 pi. Here it is that n phi 0. Here is phi 0 means that phi 0 is defined by h over e star, and it means that it is very important, and especially the phi 0 we call it as a flux quantum. In quantum mechanics, and especially in the superconducting materials, superconductor is the macroscopic quantum phenomena, and in the superconducting materials, and magnetic field is quantized as magnetic flux, and the lowest unit of magnetic flux is the flux quantum, and the flux quantum is about h over e star, and therefore it is very important. And from this equation, say that the flux, the sum of the flux and the current density is quantized. It is a flux quantization. It means that flux quantization, and it is a flux quantum. Magnetic flux is quantized. Magnetic flux is quantized in superconducting materials. It is very important, and therefore you should remember the result, and also, and therefore the flux quantum is like we call it as vortex, magnetic vortex, and we will deal with the magnetic vortex dynamics in the real investigation of the superconducting materials. And the magnetic vortex is very important topic in superconducting materials. And next, from this, we will deal with the penetration depths, and the penetration depths in terms of this equation. And let's think about the penetration depths. In the first case, we assume that divergence A equal to 0 case, and also in other words, and the magnetic vector potential is like AYX, and it is a J direction, and also it means that in superconducting materials, and here is the X, there is magnetic vector potential. Magnetic vector potential, it is a y component of magnetic vector potential, and it is inside. This is a superconducting state, and this is normal metallic state, normal metallic water vacuum state, and it is as a function of x. And also here we say that anyway, then the x direction I direction can be preferable, and anyway then you can choose any direction. Here the magnetic vector potential can be calculated and insert this equation, and this result is the flux quantization in the superheating state. And also in this case, let's consider for the to evaluate line integral, because this equation calculating the line integral. Therefore, we should calculate the line integral for vector potential and also carrier density. And therefore, let's think about x and y plane. And there is a closed square and a closed rectangular counter, and also the width is L. And here is this is x0 and it is x1. And in semi-infinite case, is that x equal to x0 and also x1 goes to infinity, and therefore, and also inside a superconductor, we know that the current density equal to 0, and current here we assume that there is no in the Meissner state, means that magnetic flux expands to the outside of superconducting materials, and therefore inside the superconductor magnetic vector potential also equal to 0 inside the superconductor. Here the J and magnetic vector potential equal to 0 inside a superconductor case. And also this term and this term, this line contribution cancel with each other. Therefore, only this line, only this region should be considered, and this line and this line cancel with each other, and this term goes to 0 because magnetic vector potential and also the carrier density equal to 0 inside the superconductor. Therefore, the first line should be considered. And also, let's think about that. Let's think about this equation. Yeah, let's think about this equation and also calculate using this line 1. And the first term, the line integral say that it is a length L, and m star, and carrier density is jy direction, jy component, and x0, and it is e star square and also phi x0 square. It is first term. And second term, let's think about the second term. It is plus a y component, and at x0 it is n phi 0, and this one, and it is the result of the magnetic flux quantization. Let's think about that if n equal to 0, and basically gradient zeta LDL equal to 2 pi n, and because n equal to 0 and it is 0. It means that zeta is constant. Zeta is constant means that phi gradient phi and the phi gradient phi star equal to each other, and therefore the first term cancel. This term goes out, and anyway from this equation for in the case for the n equal to 0 case, and here jy x can be calculated like minus e star square phi x square over m star a y x0. Let's define it as equation A. Then because we know that J is that 1 over mu 0 and the curl B, and B is that the curl A, and plus it is E star square phi square over M star A equal to 0 from the above equation. And also because we assume that the gradient vector potential equal to 0, and also from this, and also it is gradient A minus Laplacian A is equal to 0, therefore it is Laplacian A. Here in one-dimensional case, and let's think about the one-dimensional case. It is that d square A. In this case, then the vector potential is the y component as a function of x. The x square equal to minus here mu 0 e star square phi x absolute value square over m star a y x. Here we can define that it is penetration depth and also a y x, and here let's define that it is a penetration depth, 1 over penetration depth, the square, and it is lambda L square. Then here the penetration depth is defined by that lambda L square is that m star over mu 0 e star square phi infinity square. And then in this case, the solution of this equation is that AYX component is that A0 exponential minus x over lambda L. Here it shows that the magnetic vector potential in the Y component, and they should have the exponential behavior like this, and the behavior is that the A0 exponential minus x over lambda L behavior, and there is a penetration depth. For example, there can be defined by the penetration depth as the logarithmic inverse distance, and also we can say that it is magnetic vector potential decreases exponentially. Because magnetic vector potential decreases exponentially, the magnetic field also can decrease, and also therefore the magnetic field also, because we know that the magnetic field is the curl A, and curl A, it has the y component, and therefore in the y component, and the curl A shows that the g component of the magnetic field is that the derivative here is minus lambda L over A0 exponential minus x over lambda L. Therefore, the magnetic field also has the B0 exponential minus x over lambda L. And here x is lower than infinity and larger than coherence length. Therefore, the magnetic field also shows the magnetic vector potential and magnetic field in g direction, also shows that exponential decrease at the surface, and it is natural. And also, and we can think about that. We can think about the critical current, and we know from the equation A, equation A shows that because we define that it is penetration depth. Penetration depth is here, and also therefore E star square phi square over m star is that mu zero lambda L square. Therefore it is from the equation A. From the equation A shows that mu zero lambda L square JYX has the minus AYX. Here, and let's consider in this case in the second derivative with the x, then AYX is that minus mu zero lambda L square d square and dx square JYX. Then from this equation, and it is also lambda L square AYX over lambda L square, and also it is that because it is from this equation, and also lambda L square lambda AYX over lambda L square means that it is minus mu zero JYX. Therefore from these two equations, and we can say that, and d square dx square JYX also has the JYX over lambda L square. Therefore JYX also has the J0 exponential minus x over lambda L. Here it is also carrier density also decreases exponentially, and it is consistent from the London equation. We already calculated the London equation in terms of phenomenological theory. Anyway, the Ginzburg-Landau theory is also phenomenological theory, but it considers for the Gibbs energy consideration, minimizing of Gibbs free energy, and all the parameter introduction gives the same result with the London equation.